Good morning, good afternoon, good evening, wherever you are. Today, what we're going to do is our last lesson of circle geometry. We're going to learn 8.4 cyclical quadrilaterals. Quadrilaterals, just a reminder, we've talked about this before, but it's like a four-sided figure, right? Four sides. So what we're going to do is we're going to have now these quadrilaterals inside of circles, and we're going to see some traits that come with them and some rules that we're going to use to be able to find angles again within inside of a circle. Let's see. So first rule, we got two examples down here. We'll look at this first one. We have a circle, and then we have a quadrilateral inside of that circle. The first rule we're going to learn is that when you have opposite corners like this, those are opposite corners. These are also opposite corners. Then those opposite corners must add to be 180 degrees. So in this case, angle A plus angle C would have to equal 180 degrees. If you look at the other one, blue, that means angle B plus angle D must equal 180 degrees. This rule of the angles opposite of each other adding up to be 180 we'll refer to as the opposite angle rule. That's kind of what I call it. The next rule that we have has to do with something called an interior angle and an interior angle and an exterior angle. So interior angles are angles that are inside of the quadrilateral. So for instance, this is an interior angle, this is an interior angle, this is an interior angle, and this is an interior angle. Exterior angles are angles that are created by extending the lines and making an angle outside of the quadrilateral. So for instance, if I took my lines and I extended them so that they look like this, and I had this like quadrilateral with all these extended lines, then the angles that are outside of the quadrilateral are exterior angles. So for instance, if we're looking at this, this is an exterior angle. 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 And over here we have two more exterior angles. Okay, they still connect to the quadrilateral, right? But they're just outside of that quadrilateral. The rule that we're going to learn with this is that when you have an interior angle, the opposite exterior angle will be the same thing. So if I'm looking at this, where I put that star, is an interior angle. If I go to the other side of the quadrilateral and then I look at the exterior angles, those would actually equal the same thing. So all of those angles are the same. In this case, we have angle beta equals angle alpha. I think that's what those symbols are called. Greek letters. I don't know. I'm not taking Greek class. I teach math. So those opposite angles, when one is interior, one is exterior, add to be 180. Perfect. Basically, all we're going to do now is we're going to apply those two rules to a bunch of questions so you can see how they work. Look at this first question. We're going to try to find angle X and angle Y. The best rule to use, I think, or the easiest one to use, is that opposite angles must add to be 180. So if I look here, that's an opposite set of angles. That means 99 plus X should equal 180. That's the rule. We could then solve X by just subtracting 99 from 180. That means in this case, X equals 81 degrees. For Y, we notice that Y is opposite of 74, and they're both interior angles. So that means if they should add to be 180, I'm just going to do a shortcut here. That means if I take 180 and I subtract 74, it should equal Y. Just a bit of a shortcut. If you do that, you should get 106 degrees is equal to y. Easy, right? That's the best. That's probably the easiest rule that we apply. As long as you can identify opposite angles that are both interior, it's a simple rule. So let's try this one over here. Let's try to find B first. So if I look, B is opposite of 140. That means if I take 180 degrees and I subtract 140 degrees, it will give me angle B. That means 40 degrees equals angle B. The next pair of opposites that I see is angle A with 60. And that's a hard one to kind of see that those are opposites, just because the quadrilateral is on such a weird angle. But they are opposite, so we can do our trick for that. 180 degrees minus 60 degrees should equal A degrees. Sorry, my A is so messy. My pen did not register there. 180 minus 120 or 180 minus 60 equals 120. So that means angle A is 120 degrees. Wonderful. Let's do a couple harder questions. So looking at C here, we got a few different sets of angles here. We also got some weird things going on. The first thing I want to do is I want to show you that we do have two quadrilaterals here. The first quadrilateral that we have is this little guy right here. The second quadrilateral we have is this bigger one. And the rules that we learned will apply to both quadrilaterals. So the very first thing that we could do is we could figure out, hey, this right here, oh, sorry, I'm on my shapes. This right here is a pair of opposite angles that are interior. That means they should add to be 180. Now, when people do that and they're like, okay, so if I do 180 and I subtract 55, you might not want to write this down, just for the record. That tells me that angle 3, I shouldn't call that angle 3. I don't like that. That means that angle of number 3 over there should equal 180 minus 55, should equal 125 degrees. Now, we know that 125 degrees is a pretty big angle, right? So if like this is 90 degrees, making that perfect 90 right there, 125 should be pretty open angle. And if you look at my question, I mean, it's not even close to being something that's that open. So that right there should be kind of alarming. Now, our diagrams aren't always to scale, so it's not a foolproof method. But when it's that far off, like something feels wrong, looks wrong, it probably is wrong. The problem here is that our blue quadrilateral doesn't get to follow the rules we just learned. And the reason why it doesn't get to follow the rules we just learned is because not all 4 corners or vertices are on the outside of the circle. So if you look, that blue quadrilateral goes to the middle. It doesn't go to the outside edge. And our rules only work when you're going to the outside edge. So this blue quadrilateral basically means nothing to us when it comes to our quadrilateral rules. So the only quadrilateral we can work with is this red one. Tricky, I know. Okay, so to work with this red one, first thing I'm going to notice is, hey, I've got some opposite sides here. I've got 2 and 65. Those are opposites. I'm going to use my opposite trick to figure out what angle 2 would equal. I go 180 degrees. I subtract 65 degrees. That equals 115 degrees. So angle 2 is 115 degrees. Perfect. Let's put that in there. 115 degrees. Now I'm a bit stumped. So if I went to solve for angle 3 and I tried to use my opposite rule, I can't because angle 3 is inside that smaller quadrilateral. not as big ones. So I can't actually solve for 3 right now by the looks of it. If I look to solve angle 1's not even a part of one of my vertices or one of my corners on the quadrilateral. So that kind of tells me right away something's fishy. What I am going to do is I'm going to remember some of my rules from the other day. And one of my rules was that when you have central angles and inscribed angles, the central angle is always double the inscribed angle. And what that means is that if you had a point on a circle and another point on a circle, and I could get from one point to the other by going outside and then to it, that was called an inscribed angle. And it would be half the size as if I went from one point to the center of the circle to the other point. That means that this angle should be 2 times the inscribed angle of 65. If we try that, 2 times 65 degrees equals 130 degrees. So this angle in here must be 130 degrees. If you don't remember that, that's using our inscribed angles and our central tendency angles. Okay, now that we have that solved, I'm just going to erase some of these lines. We're stuck looking for 3 over there. Angle 3. And that's it's going to be a tricky one. 130 degrees from 1. It's going to be found using another rule that we talked about a long time ago. Maybe we forgot it. And that rule is that if you have a quadrilateral, and it can be any quadrilateral, so this doesn't have to be quadrilaterals that touch the outside of the circle. This could be any quadrilateral, that all the angles added together equals 360 degrees. And we look there, we have that nice little red quadrilateral, so we should be able to add those angles up to all be 360. The way that this rule is going to be helpful is we're going to take 360 degrees, we're going to subtract away the 3 angles we do know, so 55 degrees, subtract away 130 degrees, and subtract away 115 degrees. And that will tell us what our missing 4th angle is. So in our calculator, we go 360 minus 55 minus 130 minus 115, and we get that last angle must be 60 degrees. Awesome. That's a tricky one. So we had to use our interior quadrilateral rule. We had to use our central angles and our inscribed angle rule. And we had to then use our all quadrilaterals add to 360 rule. So that's a hard question. Let's slide over here to D. So if we look at D, we can see we have a quadrilateral. The quadrilateral is on the outside here. This is a quadrilateral that touches all corners to the outside of the circle. That means we can use our rules we've learned today. So let's do our simple rule that we're already pretty good at, and that's that opposite corners will add to be 180. So I can go 180 minus 80 to get C. It means 100 equals C. I could then use that rule again for these angles right here because they're opposite and both on the interior. So 180 minus 110 would equal angle B. That means 70 equals B. Awesome. Our last one, angle A. This angle here is an exterior angle. It's exterior because it's on the outside of the quadrilateral. It's what happens when you extend one of the lines. We learned that exterior angles are equal to the opposite interior angle. So the opposite of the interior for angle A, opposite means you're going across, and now I want to go to the inside. That means 110 degrees is my opposite interior angle to that exterior angle. Now, there is another trick that we could use that we've learned from before to be able to find angle A. So I'm just going to talk about it. That trick has to do with the fact that we know what angle B is. So we know that angle B is 70 degrees. And the trick comes from remembering that if you have a straight line, the angle that goes all the way across that straight line should equal 180 degrees. That means this missing angle on the other side of 70 should add to be 180. So if we did 180 and we subtracted 70, we get 110 degrees, which is the same answer that we got before using our exterior-interior rule. But I like using that 180 rule with straight lines. So you're probably going to see me use that a few more times. All right. Let's try 2 more examples. So if we look at example E here, let's start off by drawing our quadrilateral just so we can all see it. Our quadrilateral that goes from all the corners, right? Because we learned on a previous example that you have to be on the edges of the circle with your corners. That's our only quadrilateral that we have. We have some angles that match up nicely, so let's do those ones first because that's easy. So we have our opposite angle rule right here. Opposite angles must add up to be 180. That means we could go 180 minus the 100 that we know, and that will give me my first angle, which is 80 degrees. Awesome. Knowing that that angle right there is 80 degrees, I'm going to use my trick that this is a straight line, and the angle on a straight line should add up to be 180 degrees. That means if I do 180 and I subtract the 80 degrees that I do have, it will give me this missing angle right here, which is 100 degrees. I could also have used my interior-exterior rule. So if we look, if I wanted to figure out angle 3, there's another way to do it. I could have realized that this exterior angle, number 3, is the same as this interior opposite angle of 100. Okay, perfect. Now, our last one over here is this 45, which is going to be a little bit trickier to solve. And the reason why it's trickier to solve is it doesn't really fit into any of our quadrilateral rules. Our problem is that this 45 degree isn't the entire angle in the quadrilateral, and this number 2 is not the entire thing in the quadrilateral either. The next thing that makes it tricky is it's not an inscribed angle that we could connect with any central angle. It's not an inscribed angle we could connect to any other inscribed angles. So we're at a bit of a loss when it comes to all of our rules. This one requires us to use a different trick. And that trick is remembering that when you have a triangle, which I have here, all triangles should add up to be 180. So if I took all those angles, they should add to be 180. This means I can figure out angle 2 by going 180 and subtracting the other 2 angles in the triangle. If we do that, I believe we should get 55 as our answer. So angle 2 is 55 degrees. I think that's the only way you can get that one. Awesome. F. So we look over here. We got a couple different ones we're looking for. We're looking for D and E. We're going to start off, because the quadrilateral rules are kind of the easier rules to work with. Let's see if we can do that and make our lives easy. So we have a quadrilateral here. I believe it's our only quadrilateral where all the corners are on the edge of the circle. So it's the only quadrilateral we can use our quadrilateral rules with. Let's see what we got. We're looking for 2 little chunks, this one here and this one here, so that's kind of hard. We did get an exterior angle of 130, so this exterior angle should be equal to the interior angle on the opposite side, so it should be equal to this whole thing. So that entire angle equals 180 minus 130. Oh, sorry. I lied. I'm doing my interior angle. It should equal the same thing because one's an interior, one's an exterior, so it should equal 130 degrees. That doesn't really help us right now. It might help us in the future because we should know that E plus D equals 130. If I'm looking at this now, I don't know if there's much else that's going to help us when it comes to our quadrilateral rules. So that's a little tricky. So what we're going to do instead now is we're going to see if we can't use any of our inscribed rules. So the other thing they gave us was they gave us this 70 degrees right here. That 70 degrees is an inscribed angle, meaning that if I went from this point over here and tried to get to this point over here, I could do that by going up to that spot and then down to that spot. And that creates 70 degrees. And we know from, I believe it was last lesson, 8.3, that all inscribed angles that get you from one point to the same point are equal. So that means if I took from that first point and I went out here, and then I went back to this second point over there, that inscribed angle, D, should be the same thing as this inscribed angle of 70 degrees. Because that's our inscribed angle rule. Must be the same thing. Now, because I know that in there is 70 degrees, and I know that the entire thing should be 180, I can figure out what E is. I can figure out what E is by going 130, which is what that whole angle should be, and subtracting away the 70 degrees. That gives me 60 degrees. I apologize. I think I said 180 there when I meant 130. Awesome. So looking at that question, we use our interior-exterior rule to get 130 degrees, the green one. We then use our inscribed angle rule to get 70 degrees for D. And then we used our 130 minus 70 to figure out the missing part of E. Okay, 2 left. Let's look at this one first. Where to start? So, when starting with this, let's try. We can try to start with the quadrilateral. It might not help us, but I just like working with the quadrilateral rules. So we've got this quadrilateral on the outside here. That's the only quadrilateral we can work with because that's the only one where the corners are all going to the same spot or all going to the outside edge of the circle. They didn't tell us much about this quadrilateral. All they told us was this guy over here is 107. That means the opposite corner should add up to be 180. So it might not help us, but we're going to do it anyway. 180 minus 107 gives us 73 degrees. That means in here should add up to be 73 degrees. Cool. When I look at the rest of that quadrilateral, there's not much I can really do. So that's going to do it for my quadrilateral, at least at this point. The next thing I'm going to do is I'm going to look at what they've given me. They've given me 86 degrees right here. So I'm going to realize, hey, that 86 degrees is a central angle from this point to this point. So if I could find an inscribed angle that gets me from one point to the other point, then I know there's a relationship between those central and inscribed angles. And there is an inscribed angle here. If I look here to here, that is an inscribed angle that relates to my central angle. We know that central angles are always twice the size of the inscribed angle. So that means what I could do is I could divide by 2 or times it by 0.5 to get the inscribed angle, which is 43 degrees. So angle 1 is 43 degrees. And that's using my central angle rule. Central and inscribed angle rule. Okay. Now, figure out angle 2 and angle 3. This is a very hard one. If this was on a test, I would expect very few people to remember this rule, even though it's a simple rule we learned a long time ago, just because there's so many rules now, right? And it's not a rule we use a lot. So if you look down here in the circle, we have all kinds of triangles going on. I'm just going to erase some lines to make it a little bit more clear. Okay, the triangle I want you to notice is this one. Now, there's something special about that triangle that isn't obvious. And what's special about that triangle is that two of the side lengths are both radiuses, meaning they both go from the edge of the circle to the center. That means that those two side lengths are the exact same side length, making this triangle an isosceles triangle. When you have an isosceles triangle, that means that the two angles right here and here must equal each other. This means I could say that 180 minus 86 would give me what the other two angles must add up to be, which is 94 degrees. But that's both of these angles add to be 94 degrees. So if I wanted to find just one of those angles, I would have to divide that by 2. Split it in half. And that would give me 47 degrees. That means angle 2 is 47 degrees. Awesome. With that knowledge, I can then find angle 3. The way I can find angle 3 is by remembering that this entire angle was 73. I now have this little piece of 47. If I want to find the missing side over here, then all I need to do is go 73 degrees minus 47 degrees. And that will give me my missing side of 26 degrees. Awesome. That's a hard one. Okay, this one's not so hard. It's just algebra. So we're going to use a couple different rules. First rule we're going to use is we're going to remember that our opposites on the inside of a quadrilateral should add to be 180. That means if I took 105 degrees, it's not letting me write. There we go. And I added the opposite angle. And in this case, the opposite angle is 8x minus 5. That should equal 180 degrees. Right? That's our opposite angle rule. When we have those opposite angles, we can add them together to equal 180. Now, in this case, we're trying to solve for x. So this is a bit of review from the previous unit on how to solve for a variable when you have an equation. I'm trying to solve for x means I want to get x by itself. To get x by itself, I want to move everything to the other side of x. So the things I want to move away, I want to move away this plus 5, and I want to move away this 105. And I want to move them to the other side of the equation. Before I do that, I'm going to realize that those are like terms, and they can add together. So 105 degrees minus 5 degrees is 100 degrees. And then I still have my plus 8x, and it still equals 180 degrees. The way that we move things is by using opposite operations. So now I can move that 100 degrees to the other side by subtracting 100 degrees from both sides. That means that 8x equals 80 degrees. To get rid of the 8, the opposite operation would be dividing by 8, because that means multiply, right? If there's nothing in between a number and a letter, that's multiplication. 8's cancel out, so I have x equals 10 degrees. That's my first answer. Wonderful. My second answer is going to come from realizing that these are now opposite angles. So if I did 4y plus 14 plus the opposite angle of 7y plus 1, that should equal 180 degrees. My goal is to solve for y. The first thing I'm going to do is realize I have some like terms, right? I have 4y plus 7y. When we're adding variables, 4 of something plus 7 of something equals 11 of that something, so 11y. I then have some constants. I have 14 plus 1. That adds together to be 15. And it equals 180 degrees. I then can work towards getting y by itself. So I'm going to move things away from y. I'm going to subtract 15 from both sides. That gives me 11y equals 165 degrees. I'm then going to divide both sides by 11. 165 divided by 11 is a nice, cool 15 degrees. So y equals 15 degrees. Awesome. That question is a little bit more review of our algebra that we learned in Unit 6, I believe. All the units are starting to blend together now. Awesome. You're done circle geometry. Just a reminder, circle geometry is very challenging, and it comes from lots and lots of experience to be able to get good at it. So practice your circle geometry so that you can start to get good at it. I know it's hard and frustrating, but you just have to keep on practicing until you start to see rules and patterns. Wonderful. Best of luck. Talk to you soon. Hopefully I see you soon. If you need help with anything, reach out to me.